All right. So today we are going to be we are going to continue talking about MIPS instruction set architecture. This is part 2 of the ISA conversation that we started during the last class. So we'll continue that. So a few highlights from last time. We were looking at assembly level instructions over here and their meaning, right? What do they actually mean in terms of operations? So if we start all the way to the top, I'm going to quickly go through them. This should serve as a refresher from last time. Here we have a add instruction and subtract instruction. These two are arithmetic instructions of the R type. And the good thing about these R-type instructions is that our operands are part of the register file, right? So that makes things a lot faster because accessing the memory will be slower. So here we have an add. So what is it going to do? It's going to take contents of S2, contents of S3, and it's going to add them up and then put the result in S1. S2, a 32-bit register in the register file. Same thing applies for S3 and the same thing applies for S1. They're all 32-bit registers and the instruction is also a 32-bit instruction, right? So the instruction itself, which is R type, we talked about the format in the previous class. It has an opcode field, source registers, the destination register, shift amount, and the function code, right? So but in total, if you add all the bits, it comes to 32 bits. So the instruction, the registers, all consistent with 32 bits. So what does it mean? We can write this as S2 plus S3 goes into S1. Now when you come to subtraction, S2 minus S3 goes into S1. Now when you go to the next two instructions, actually the next 4 instructions are of the I type. So all these guys are I-type instructions. So first we have load word, store word, branch when not equal, branch when equal. So for all these things, we have a 16-bit address field that we can use, and that is called either a immediate 16-bit immediate or a 16-bit base address. So it will be a 16-bit base address as far as the load word and the store word instructions are concerned, because we need to access memory. So we need to have some address, whether it is the write address or the read address, doesn't matter. It has to be a memory address. So that is going to be our 16-bit base address. We are going to store that address in S2. Then we are going to execute the load word or store word, right? So whatever we have in S2, we are going to add an offset to that, which is in this case 100. And whatever this results, this is going to be a memory address. And at that memory address, we are going to read and then move the contents of that memory address to this particular register, in this case S1. So S1 will become whatever is at the memory location, the address is contents of S2 plus 100. The question online, for the load word and store word, can the offset be a register? No, it can't be a register. So the offset has to be, something that it's a constant, which is part of the instruction. So something like the add I instruction, the add immediate instruction, which should include a constant or the immediate constant as part of the instruction. So similarly, load word has to have that 100, that offset has to be part of the instruction itself. So to answer your question directly, no, it cannot be part of the register. However, you can do it still, right? Like you would have to work around that, right? So you can say, all right, I'm going to store 100 in a certain register, and then that's how I will get that 100. But then as far as the instruction itself goes, that has to be a constant. Now, coming to the store word, things are going to happen in the similar manner, but in the opposite direction. So over here, we are storing word. Where are you storing? In the memory. What is the address? Take contents of S2 add an offset to that, that's your address. So whatever you have in S1, push that data into memory at that particular location, right? So it's going to go memory to, it's going to go S1 to memory in that case, storing word. Now load word and store word are loading and storing one word. And we know from the MIPS ISA conversation from before that you can still address using bytes, right? It's a byte addressable instruction set. However, it is word aligned, right? So that is something that is kind of important to keep in mind. So byte addressable, and word aligned. So as far as instructions are concerned or programs are concerned, it becomes particularly important to be word aligned. So that means that programs or instructions cannot be, half of it cannot be in one word and the other half cannot be in the other word. They have to be word aligned. All right, let's move on. The next I-type instruction here is the branch when not equal. So it will compare the contents of 32-bit constants of S4 and S5. If it's not equal, then it will go to some L. L right now is serving as our label, but it is some part in the memory which has another instruction located at that, right? So it's like a jump command or jump function in C, for example. So go to L if S1 is not equal to S5. That's what it means. Well, what if it's not? What if it is equal? If it is equal, it is not going to jump, but instead it is just going to work on the next instruction, right? Whatever follows that branch not equal, it's going to work on that. So there's another question in the chat box. So $S2 plus 100 refers to an address and not a value, right? It refers to an address. You got it. So the memory, where in the memory, you need to give the address, right? So it refers to the address. You're absolutely right. Let me highlight that. So this is an address. And then this is contents at that address. Memory contents at that address. And the same thing applies for even in the store, right? So I said branch when not equal. So if it is not equal, then it jumps to some location L in the memory and start executing instructions over there. But if it is equal, then it will not jump. Instead, it will just jump to the next instruction. So PC will become PC plus 4 and you continue working on the program. So a quick question here. L in this case is the location it jumps to, right? So we also talked about the fact that it is word aligned. So instructions or programs need to be word aligned, right? So what that means is when I jump, I'm not going to jump in the middle of a word. I have to jump to an integer number word, right? I cannot jump to byte 1 or byte 2 of a word. I need to jump to word 1 or word 2 or word 3, which essentially tells me that the jump label can be, or in fact it should be, a word. It should be specified in words instead of bytes, because I'm never going to jump in the middle of a word. I'm just going to go to a word. What is a word? Well, let's just refresh that over here as well. One word equals what? 4 bytes equals what? 2 half words equals what? 32 bits. Right. So we are still addressing things byte wise, but we are aligning things word wise. Last one. So BEQ, branch when equal, very similar to branch when not equal, except that it is checking for equality as opposed to inequality. S1, S4, contents of S4 and S5, if they are equal, jump to L. If they are not equal, then just continue with our program. It's going to go to the next instruction in that memory sequence. So PC will become PC plus 4 and it'll jump. It will not jump. The last instruction here is a J type instruction. There are only a few jump instructions. There is J, there is JAL, which is jump and link. We'll take a look at that today. So those instructions have a slightly different format. In that, I only need to give the opcode and then give a 26-bit address. Why do we care about two half words? Well, it's just a different way of representing the 32 bits. Now, why do we care about that? Well, different versions of MIPS have different addressing schemes. So, for example, we have things that are byte addressable. Sometimes it could be half word addressable, or a byte addressable, or word addressable. So it depends on the version of MIPS we are using, but in this case, we are focusing on byte addressable memory. Next, what do we have? Oh, at the bottom here, we just have a format. So it's not nothing new there, just formats of different R, I, and J instructions. Let's move. Another question I want to ask here is this. Can this number, let me highlight it in pink. Can this number be 2? Can this be 2? The offset? No. What does it have to be? It has to be a multiple of 4. You got it. So the reason why it has to be a multiple of 4 is because when you do the load word, you're doing a word aligned load operation. You're not loading things midway through the word. Divisible by 4. Yeah. It is the same thing as saying 100 is a multiple of 4 and it is divisible by 4, right? Like, so it has to be 0 or 4 or 8. 0 works as well. So 0 essentially means no offset, right? No offset. Take whatever you have at the address at S2 and move it into S1. Could you repeat why it must be a multiple of 4? Sure. So actually I can do so we have a byte addressable memory and word aligned memory, right? So how can I do this? I can move this over here. So I'm gonna share my screen quickly so that you guys can see which one are you doing? Oh, not this. Give me 1 second, you guys. Here, and not this. All right, so hopefully you guys can see this. And I'm just going to go back to my Mars simulator just to illustrate what that I mean. Open. So I encourage you guys to get this simulator. It is free, but it can be helpful to. So I can say, all right, let me do a load word here, LW, and I'll try to load. Let's see, in $S1, I will try to 0 and $S2, right? So this is no offset. Whatever is in S2 right now, what is S2? S2 is all zeros, right? Bunch of zeros. I can just change this to maybe 001, maybe something like that. So I've just changed S2 to some arbitrary sequence. Now what is it going to do? It's going to look at the S2 right? And it's going to add 0 to it. It's going to try to load from that memory location the contents into S1, right? That's what I would expect. So I said 0. Let's see if this works. So I'm going to go into run. Oh, sorry, I need to save it. So let's save it first. To and then I can assemble it. So when I assemble it, it has converted that instruction into all the 32-bit format as an instruction. So it's looking good so far. Assembly was done properly. And then if I do run, right, and I can step through this. I only have one instruction, so I can just run through it. So when I run this, oh, the address is out of range. So there is nothing over there, which has stopped me from doing that. But it assembled clearly, right? It wouldn't if I had a different program. So for example, if I go back and change this to 1 instead of 0, and then try to assemble it, it is going to give me multiple errors, right? You see it says fetch address not aligned on word boundary 1. So the word alignment is not going to work because now you are looking for byte 1 or byte 2. You can only go for word 0, word 1, word 2, and so on. A word is comprising of 4 bytes. And if at each word you call that like byte 0, byte 1, byte 2, byte 3, you cannot load things in the middle. A word is 4 bytes, yes. So it's because I have a word aligned memory. All right, let me share this again. So I encourage you guys to kind of install this simulator or any other MIP simulator. There are several of them that are available for free. So you can have a better understanding of MIPS instructions with the help of that. You can actually see them in how they work. Let's see. So that was why this has to be a multiple of 4, right? So 0 works, 1 doesn't work, 2 doesn't work, 3 doesn't work, 4 would work. So every multiple of 4 from then on would work. And the same applies for store word as well. Okay, so let's continue. Here we have a loop example. The loop example that you are looking at is in the form of a C code. And quickly, there's a simple for loop here. We have initialized j to 0, and then we are running a for loop. In this case, we start with I equals 1, and then we come out of this for loop when I is so we stay in this loop until I is less than or equal to 10. And in each iteration, we are incrementing I by 1. So it means that it's going to start at 1 and it is going to go on 10 times, right? And when it is 11, that's when it's going to come out. And in each iteration, you are essentially accumulating on j. So you start off with j as 0, and then you add 1 to it, and add 2 to it in the second iteration, and 3 to it in the third iteration, and so on, right? So you're just writing an accumulator to add up the first 10 integers in this case. So j would have the actual accumulated sum. So if this is your C code, how would you translate that into a MIPS code? Well, for that, instead of going directly from C to MIPS, let's try to look at how do those instructions look like in the form of a pseudo code, right? So before we write MIPS, let's write some things that are a little bit more organized, which will help us write the MIPS code for this. So start with j is 0. So we have taken care of that. I is 0. We have initialized I as 1 and I is 1 here. Then we write a loop. Loop in this case just refers to the label for that particular address location where there is a if condition, right? The loop here is a label to that. It's a addressing label. So The instruction over there is if I equals 11, jump to end. Where is end? End is right here. So that is after this particular loop, right? It's skipping over it. So end is referring to the label just after that loop. And then loop over here is kind of used here again. That's your loop, right? So if I equals 11, jump to end. Well, is it? It's 1 right now. So it's going to ignore that condition because it didn't satisfy, and it's going to start working on what is inside that if condition. What is it? J equals j plus I. So that's your first iteration of this particular statement. The next one is I equals I plus 1. So that's your incrementing your I, which is next. And then you jump back to that loop. So you jump back to that loop right there. So as you can see here, each of these statements can be easily translated into a MIPS code, right? So what instruction would you use to do this? Any ideas? For these two, actually. Add with 2 zeros. Sure, I would have done it using add I. Add I, here I have a constant, right? So I have a 0 as a constant, 1 as a constant. So I could have said add I $S0, for example, where S0 may be referring to J. And then I could do $0, which is a constant 0, and then 0. Does add I call? No, it doesn't. So add I is an I type instruction that is used to do very quick addition operations in the case of one operand being a constant. So it turns out that adding a constant is often used in programs. So you don't even have to go to memory. Load and store word, those go to the memory. I don't have to go to the memory in this case. I just look at the register file, perform the operation using the ALU, and I'm done. Save that result back into the register file. I don't need to look at the memory. So I would have done add I in this case. And the same thing I would have done even for the next one, for I. So I would have used add I, maybe a different register, not a maybe, has to be a different register because it's a different variable. $0 and 1, right? Done. So what does this do? It adds 0 to 0 and saves the result in S0. In this case, I'm saying S0 is kind of like my J, right? It's representing J, and S1 is representing I. Now, if you look at if condition, what would you have used to which MIPS instruction would you use instead of if? If this equals 11, what would you have used? Branch if equal, and if you want, you could have also used branch if not equal. You will have to just manipulate it a little bit, but you could have used either of these inequality or equality checking branch instructions, right? Okay, how about next? J equals J plus I. What instruction there? Has to be add, right? Okay. Add instruction there. How about this guy? I equals I plus 1. What would you use there? Add I, brilliant. What instruction would you use there? Jump. Done. You see that? So now you can see, even though you have a 3-line C code, because you have written something that looks like this, which is your pseudo code, it allows you to move to the MIPS equivalent code very easily. And that's exactly what we are going to do here. We are going to take that and look at the MIPS code instruction by instruction. This guy equivalent, this guy equivalent, this guy equivalent. And it looks like the same registers have been used, the same ones that I used earlier, right? So J equals 0, right? Do that very quickly using an add I. Add immediate. Take $0, which is all zeros, add another 0 to it, which is just 0, save the result into S0, right? Very useful if you wanted to initialize a certain variable and assign it a constant, right? Things like this. This is very useful. And add I is also useful over here, right? Incrementing things by 1. Now we have got the add I here. We have got the add I instruction over there. And instead of going and looking into branch if equal, we have another temp variable that we are using because we are going to compare the value of I with that temp variable. So we are using temp as 11, which means that I'm using some temp register T0 and initializing it to 11. Do I have to use T0 here, or could I have used S2 or S3 or any other register? Can you use add for add I plus 1? So yeah, but wouldn't you have to, so that'll work, but like Kendrick says, it's going to be slower. And the main reason why it's going to be slower is because you have to store 1 somewhere, right? With 0, I have a place where I have a constant 0. So that's my that's sort of a constant register which I can use. I don't have a constant register which has 31 zeros followed by a 1. Like I don't have that. Like I don't have a 1 register. I have a 0 register. I don't have a 1 register. So I'm going to have to put a 1 into one of the registers, right? Like I could do that. So let's talk about that. I equals I plus 1, right? So for this to work using add, I would need to say add I, right? $S3, $0, 1, right? That's making S3 1, followed by saying add I $S1, $S1, $S3. Sure, I can do that, but it's going to require 2 instructions in this case, right? Like why do this when I can simply do this? Does add I not call store word to save the new value? No. So when you're looking at add I or add or subtract or and or all these operations, they never go to the memory. So let me kind of touch this. So here I have R type instructions here, right? So what are some examples? Add, subtract, there is and there are many R type instructions, arithmetic and logical operations, right? So in that case, what is happening? Well, I have a register file here, all 32 registers, and I have a very big memory here, right? For R type instructions, I don't need to go to memory at all. I need to use registers from the register file and the ALU, right? So the ALU is sort of over here. I can take things from here, go to the ALU and store things back into the register file. I never need, I don't need to go to memory at all. You see that? And the only time I need to go to the memory is when I am doing a load word or store word. And based on that, you can also comment about the speed of operations when you're doing R type instructions, because you are looking at a small register set. Things are going to be much faster, and things are going to become slower as you move towards memory accesses. So in general, you can say, all right, my register access time is much smaller than memory access time. And you can relate to that by saying, all right, which one is faster, accessing the RAM or accessing the hard disk? Which one is faster? I hope you guys all say, yeah, accessing the RAM is much faster, right? And accessing the cache memory is even faster, which is why we have that in the first place. So what is different between a hard disk and a RAM and a cache? Well, the smaller the size, the faster the memory. So register file is going to be much faster than your relatively big main memory. All right. Where were we? Oh, we were doing this. So we have initialized add I, add I, add I. J is 0, I is 1, temp is 11. Done all those three. Next, we move into this condition. Check whether I is equal to temp or not. And if it is, jump to end. This is the same pseudocode from the previous slide. So what are we doing here? Branch if equal. What are you checking? You're checking the contents of T0 and S1. What are they? T0 is representing temp, right? So let's color code this as well. T0 is representing temp. That's right there. S1 is representing I. That's right there. So I'm checking whether I equals temp or not. And if it is equal, jump to end. So where is end? It's right here. So whatever instruction is over here, it's going to jump to that instruction, right? So like next instruction, a 32-bit instruction. Now, if it is not equal, what does it do? Well, you just go to the next one then, right? So if not equal, you just do PC equals PC plus 4 and point to the next instruction, which is an add instruction, right? Which is part of the loop here, which is the thing that we are iterating over. So every time it is not equal, you stay in that loop. So what is here? Add. What are you adding? S0 is the destination. What are you adding? S0 and S1. So you're taking the current contents of J, current contents of S0, which is representing the variable J, adding it to I. So J plus I goes back into S0, which is your J, right? So J equals J plus I is what this is doing. Next, you have add I, because we need to increment I by 1, because that's how we are going, incrementing I by 1 every time until it reaches 11. So that's add I. Next, you have jump loop. So J loop, jump to the address loop. Where is it? Right here. So you go back over there, compare using the branch instruction. So for J loop, how does it know where that loop begins? So this loop is part of an address, right? So I need to provide a 26-bit sequence over here that is going to result in a 32-bit address. So that's a good question. So here, this is sort of a 32-bit address. But we know that in the J-type instructions, we have the first 6 bits for the opcode and the remaining 26 bits for the 26-bit address. So here, loop is a 26-bit address. So what we are going to do is, we are going to take 26-bit address and translate that into a 32-bit address. Well, how are you going to do that? The first thing that we are going to do is pad 2 zeros to the right. Why are you padding 2 zeros to the right? Well, because jump over here is a multiple of 4. We talked about that, right? If this is PC, this is PC plus 4, this is PC plus 8, this is PC plus 12, and so on. So that has to be a multiple of 4. So if it has to be a multiple of 4, the last 2 bit has to be a 0. So those 2 bits, I don't need to make that part of my instruction. I can just save those 2 bits, right? So those 2 bits are from there. Where are the remaining 4 bits? Because I need to make it a 32-bit address. The first 4 bit comes from the current program counter. So that's how a 26-bit address is being translated into a 32-bit address, so that you are able to jump to this location by updating the program counter with that particular 32-bit address. You see that? All right, more about jump in a little bit. All right, questions about this example. how we took a C code, looked at the pseudocode, then translated that into a MIPS code. But how do you specify that address in MIPS code? Well, like this. Jump. So I go back to my reference sheet and I take a look at jump format, right? What is the jump format? Jump is a J-type instruction. For a J-type instruction, I have first 6 bits for the opcode and then 26-bit for the address, right? So if that is the case, I'm going to look at the opcode for jump. Where is jump? Jump is right here. So I'm going to highlight this quickly. And it says for jump, the opcode is 2 in hex. 2 in hex is what? Well, wait a second. What happened here? Huh? All right. So what is 2 in hex? Bunch of zeros followed by the last two being 1 0, right? So for jump, J loop. What am I going to do? I'm going to say 0 0 0 0 1 0, right? That's my opcode, followed by a 26-bit address. That is going to make it a 32-bit instruction that goes in that space, that goes in that place. Now, when I look at this instruction, now if I'm working on this instruction, how is the processor, the core, going to work on it? Well, it's going to say, all right, I look at the opcode, it looks like it's a jump instruction, which means that it is followed by a 26-bit address. So that 26-bit address, right, bunch of zeros and ones, the first thing it's going to do is pad 2 zeros to the right. That will make it a multiple of 4, right? Which essentially means it could be pointing to one of these instructions as opposed to in the middle of a word, right? So that will make it a multiple of 4. 26 was converted into 28. I need 4 more bits. Where do I get the 4 more bits? Well, this jump instruction was written at some address, right? That was in the program counter, which means that the program counter, which has the address of the instruction that you are executing, it is going to also have a bunch of zeros and ones. So you're going to take the first 4 bits of the program counter, 4 MSBs, and you're going to pad that over there. So you've got 4 MSBs from the current program counter, 26-bit address, which was part of the instruction jump loop, then the last 4 were zeros, right? That is going to form your total 32-bit instruction. Okay, PC equals jump address. All right. So this one, PC equals jump address, essentially means that whatever you're jumping into, you're updating the program counter by that the jump address. But that jump address is not directly specified using 32 bits. It is specified using 26 bits. So there is a step in the middle, right? You have to take that 26 and then do that manipulation to convert that into a 32-bit format. All right, so hopefully that was helpful. Now, let's continue here. We are kind of slow today, so let's move on. More on some immediate or offsets of I-type instruction. When am I going to call that immediate? When am I going to call that offset? Well, if I'm using load word or store word, I'm talking about a base address and an offset. But when I'm talking about add I, I'm talking about an immediate constant. Both of these are I-type instructions. But in one case, it is going to be a 16-bit immediate. In the other case, it is going to be a 16-bit offset. So for load word and store word, the offset is signed and in bytes. So maybe you guys can help me figure out why having the offset as signed as opposed to unsigned is helpful. So what is the difference between having offset as signed versus unsigned? Can the offset be negative? That's exactly what I'm asking. So can you load or store in either direction? Load word means you are moving things from memory to the register file. Right? Load means from here to here. Loading from memory, right? Loading a word from memory. Store word means go from here to there. Let's see. Can you go back and forward in terms of moving registers? Uh, can you go back and forward in terms of moving registers? Oh yes. So here, when you're, what is the instruction here? The instruction, as we saw earlier, was what? Load word. Where are you loading from? Where are you loading from? I'm going to give you a base address in S2. You add the offset to it, right? So when you are adding the offset to an address, where are you moving? If your address is 1 in decimal and you are adding an offset to it, you only move from 1 to 101, right? You're only moving in one direction in the memory. What if you wanted to go back? What if you wanted to load? You are right now. What if you wanted to load a word that was present at a memory location that was away from S2 in the other direction, right? What does that mean? That means that if I was to give this particular offset in a negative number, as a negative number like -4, -8, and so on, it still has to be a multiple of 4, but it could have been negative, right? So if it is negative, that means you're doing S2 minus 4 or 8 and whatnot, which means that you are going, right? S2 is S2 is a register that we are using to store a base address. If you have a positive number, you are going away in one direction from the base address. If it is negative, then you are going the other way, right? So it's relative to the base address, which is why it is helpful to have it as signed as opposed to unsigned. With having signed, you can go from, if S2 is pointing to a particular memory location here, you can go above or below and then load that into register file. You guys see that? All right, so it is signed and it is provided in bytes. Well, that's clearly the it's byte addressable, right? So I'm going to still do the offset in bytes, right? 0, 4, whatever it is, but it is going to be a multiple of 4. What if the offset is too large and the memory doesn't exist? Well, you can do it. You have a range, right? So for example, if you say had n bits, right? What is the range? So n bits. Remember, we are representing this in 2's complement form. So with n bits, what is the range? Well, what is a range would be 2 raised to negative n minus 1, right? No. Negative is here. So negative 2 raised to n minus 1 to positive 2 raised to n minus 1 minus 1, right? So that would be the range of values in decimal that you could express using n bits in the signed 2's complement form, right? 2's complement. And if you're using 16 bits only for this offset, then it limits the number of bytes you can go up and down, right? So you can only go from, so in this case, we have what, 2 raised to, what is our n? N is 16, right? So what is it? Negative 2 raised to 15 to 2 raised to 15 minus 1. Can I see that? So these are those many bytes relative to the base address you can go. So there is only a range over which you can do that load word and store word relative to the address that you saved in a register. In the example that we were looking at earlier, it was our S2 register that was working as our base register, right? So you're right, because we have a limitation, it will have there is a possibility the offset to be too large, but we can do that. We can only do this load word or store word by using this. All right, let's move on to the next one. We have branch when not equal and branch when equal also as I-type instructions, in which we have a 16-bit field which is going to give us the offset. Again, the offset is signed, which means that when you branch, you can go up or down relative to the current program counter. But the offset is not mentioned in bytes, it is mentioned in words. Why is that? Why do you think it's in words? Look at this. Look at this. L over here, it doesn't need to be in bytes. It only needs to be in words. Why is that? So why is that the case? Because my instruction, when I'm branching to the next instruction. My next instruction is going to be at a word. It is never going to be in the middle of a word, right? So when I provide this 16-bit address, I need my offset in this case to be in words as opposed to bytes. You guys see that? Because when you branch to a word 0, word 1, word 2. You never branch to byte 1, byte 2. That is going to be in the middle of the word, right? Let's see. Where are we? All right. So now we still have 16 bits, and we are saying that it is signed. So what is going to be the range in terms of words? If you are working on an instruction at the program counter is what is the register which is containing the address of instruction BNE or instruction BEQ right now. Relative to PC, you can go back or you can go forward in terms of words. So you can go relative to PC, all the minus 2 raised to 15 to 2 raised to 15 minus 1, because you've got 16 bits to provide that signed offset. But whatever that number represents, it is going to be words. We'll take a look at an example for this, which will hopefully give you guys a little bit more insight into what I mean here. Now, if these are the number of words, one word equals 4 bytes. So if I adjust that into, if I want to find the range in terms of bytes, that would be PC minus 2 raised to 17, right? Because one word equals 4 bytes, which is 2 raised to 2 bytes. So if you multiply this guy by 2, this guy by 2, this guy by 4, 2 raised to 2, 2 raised to 2, 2 raised to 2, you get the range in terms of bytes, right? So program counter minus 2 raised to 17, program counter plus 2 raised to 17 minus 4 bytes. So that would be the range of branching relative to the current program counter. What does program counter stand for? Right, program counter. So so PC stands for program counter, but more importantly, it holds the address of the instruction that you're trying to execute, right? So if the program counter is pointing to 0 address, it is going to now work on 0 address, whatever instruction is present at that 0 address. Next, for add I and subtract I, which is add immediate and subtract immediate type instructions, the immediate constant is also signed. So again, signed 16-bit immediate constant. Now immediate constants. We are going to take a look at what happens when the immediate constants are small versus too large, right? Let's take a look at that. So small constants are often used almost 50% of the time on average. 50% of the operands on average are constants. So if 50% of the operations are constants, looking back at our 8 big ideas, and one of the big ideas that we talked about was to make the common case fast, which means that if you are going to do something often, you want to spend more time trying to perfect that thing, whichever one you're doing more often, right? So if you look at operations that are commonly performed, it looks like 50% of the operands that are going through these operations, 50% of them are constants. So if 50% of them are constants, let us use this add I or subtract I or these immediate constants to make them go faster, as opposed to not having these specialized type of instructions for immediate constants, right? That would not be a good way to do it. Now, what are some of the examples? Increment A by 5, increment B by 1, decrement C by 18. These are things that you could do using instructions such as add I in this case, add I in this case. I can do add I, or even I can do subtract I in this case. Doesn't matter, right? Because now I know that I can provide the operands in the signed format. So I don't need, I can do either one. Put small constants directly as operands. Okay, I can do that. Add I, one of the operands was a constant, right? For example, add I $S0, comma $0, comma 1, right? So that immediately does what? $S0 equals 1, right? That's what that does. Writes 1 into $S0. So one of the operands, which is part of the instruction, is a small constant. So directly provide it as part of the instruction. And then create hardwired registers like 0 for common constants. So for example, a 0 register which has all zeros can be used along with these immediate constants to perform operations such as incrementing something by 5, all of these operations that are commonly seen. So for small constants, it's going to work out pretty okay. Why? Because I have 16 bits to give my constant, right? So if it's a small constant like 4 or 6 or 4 here, 16 bits are more than enough to do that, right? So 16-bit signed numbers, again, they have a range. What is that range? Negative 2 raised to 15 to positive 2 raised to 15 minus 1, right? So that's a very, very big range. So if you have a small constant, sure, you can do that pretty easily using the I-type instruction. For example, this is what is this? $29. You guys know what $29 is? If I go back and take a look at $29 here, it looks like my $29 is the stack pointer, right? Let's come back. So this is saying increment the stack pointer by 4. And we'll talk about where this is useful. If you are pushing things on top of the stack or removing things from the stack, this operation will be used. Either subtract I or add I. 4 for a stack pointer is used pretty often. Next one, and I. What is and I? And I is a bitwise AND operation. So it's going to do what? It is going to take current contents of 29, which is the stack pointer register, and it is going to perform a bitwise AND operation with 6. And then the results of that bitwise AND operation are stored back into the stack pointer, indicated by $29. Now the question that you guys should be asking is this. $29, these guys are 32 bits, but the constants are provided by this 16-bit immediate field. So how are you going to do a 32-bit? This is a 32 bits, right? You need to do a bitwise AND or any other operation with 16 bits. Maybe I draw a smaller one. How is that going to work? Well, it doesn't, right? Pad it with zeros, yes. So next question is, should I pad it with zeros over here or here? Where should I pad it? So based on how the instruction is performed, the zeros are padded to the left. So 16 zeros. So that's exactly how it does it, right? So it's written up over here. The AND I means that you're doing AND operation, logical AND, this and this, between the contents of S2, if this is the instruction, S2, 32-bit register content, ANDed with bit by bit, ANDed with, right? So it's doing bit by bit with bunch of zeros and then 1 1 0 all the way to the end, and then puts the result back into $S1 because that's your first operand here. Now the same thing for OR immediate. So these are called add immediate and immediate and OR immediate. Whenever you see immediate, that means that you are or I and I, add I. These are all indicative of I-type instructions in which one of the operands is a 16-bit signed constant or signed immediate. And so that comes back to this I-type instruction, which has 16-bit constant. So this works pretty well. Small constants, right? So this is the range. So it's a pretty big range. And to call it like small constants, we can do a lot with it, right? Next, what if I wanted to do large constants? For example, what if I wanted to load a 32-bit constant instead of a 16-bit constant into a register? So the example that we are going to look at is loading a 32-bit constant into, say, a register T0. Right? Some temp register T0 has to be loaded with a 32-bit constant, like initializing temp 0 T0 with a 32-bit constant. How are you going to do this? For this, we are going to require two instructions. In the first instruction, we are going to do things for the upper 16 bits, and in the second instruction, we are going to change the lower 16 bits. Right? So we are going to do it 16 bits at a time. First we do load upper immediate, then we do OR immediate. So what does load upper immediate do? Well, load upper immediate has two things. One, it has the register, the destination register, followed by the 16-bit constant. So what does it do? It is going to look like this. It is going to take the current values of T0 and load that, it's going to take these 16 bits, put them into the upper 16 bits of T0. What about the other 16 bits in T0? It's going to make them all zeros. So that's something that can be confusing. I've had some questions about that. That when you load these 16 bits into T0, what if T0 was having some other 16 bits over here? What would happen to that? They will change to all zeros. So the moment you run this, execute this load upper immediate instruction, all the lower 16 bits of T0 will change to zeros. And I'll demonstrate that. I'll demonstrate this to you guys in just a bit using the simulator. Next, so I've got these 16 bits. How about the lower 16 bits? I'm going to perform a OR immediate I-type instruction in which I'm going to, this is straightforward, right? Bunch of zeros to the left, the 16-bit immediate to the right. It's going to go, it's going to do this or this, right? So you see T0, what is T0 is the destination. It is taking the current content of T0, which is this guy, after the load upper immediate. It is ORing that with these 16 bits, which are going to be the lower 16 bits, or these two, and then the result is this, right? So where is the result? It's in T0. So some things to keep in mind. What is the size of $T0? How many bits is $T0? How many bits is $T0? 32, right? So I'm trying to put a 32-bit constant into a 32-bit register, right? That's my goal. And I'm trying to load, I'm trying to put a 32-bit constant into a 32-bit register, and I cannot do that using add I. I cannot do that using the other instructions that I saw. The reason being, they only had space for 16-bit constants. They didn't have space for 32-bit constants. So I had to do this 16 bits at a time. I did this first, load upper immediate, then I did this next. Quick question. Can I reverse the order? Can I do upper or immediate first and then do the load immediate next? Can I change the order and still be able to do this? To do this. That is to, what do you guys think? No, cause to whether, right. So the answer here is no. The reason is when you do the load upper immediate, you make the last 16 bits 0. So if you had done OR immediate first, you got the lower 16 bits, and then you do the load upper immediate, it will make all those 16 bits to 0, right? So you can't change the order of this. It has to be upper 16 bits first, then lower 16 bits. You guys see it? Because the reason being, load upper immediate makes 16 LSBs, least significant bits, to be 0. All right, so I hope you guys see that. Now I'm gonna quickly change to a simulator view so that you guys can see me do this in the simulator. I'll show you how the assembler does it. All right, so I'm going to bring in a new program here. I did that before. All right, so can do this. All right, so here, I have two instructions over here. The first one is add immediate S300. Let me make this like 15. Sure. Now, when I make this 15, it is easily represented using 16 bits, so should be fine. But now next, what I have is the add immediate instruction in which I'm trying to add 0 to this big number. It is outside the range, and I'm putting it in S2, right? So let's see what happens when I assemble this first. So when I assemble this, it assembled successfully, but I wanted to show you guys what the assembler did over here. So for the first instruction, which was add immediate S3015, it translated that into one assembled instruction. But when I did the next instruction, which was add I S20, a big number, which is, cannot be specified using a 16-bit field, what did it do? It actually assembled it into two instructions. You see that? It did load upper immediate and then OR immediate. You see that? So it actually changed. While doing the assembly, it did that background work for us, because now we know why a 32-bit constant cannot be specified as part of the instruction, because that would be incorrect. So our assembler is kind of, taking care of that by translating that into two instructions. In this case, there are three instructions. You really need just two of them to do this. Load upper immediate and then or immediate. So I hope you guys, right? So now when I run this step by step, the first step changes as 3, it became F, right, which is 15. And then when I run this again, one more step, my AT became I'm using a reserved for assembler register in this case, which is why it is becoming 4000. It's just one way of doing it. It doesn't have to be this way. Then RI changed again, and then when you do that next, now S2 has been changed to 284548, that was in decimal, and this is 45784, that is in hex. Let's see that. So for large constants, add I wouldn't work. It actually would require load upper immediate and then OR immediate, those two instructions. Let's go back. Continue here. Now let's come to a slightly different topic here of procedure calls. Now you guys have a lot of expertise in terms of writing programs in maybe C, Java, whatever you may have used in the past, Python. You often use procedure calls, right, or functions. You write functions and then sub-functions. Why do you do that? Why do you write procedures or functions and then you call them from time to time? Why would you want to do that? Reusing the code is one, yeah. It makes your entire source code more modular. Okay, it's easier to find errors. That's another reason. Because if one aspect of your program is giving you error, that means that the problem is with that subroutine or procedure or function, whatever you want to call it. So makes things more modular, make things more readable, makes things better to troubleshoot. So it makes things more organized. So it has a lot of advantages. The reusability is another one, like Eric pointed out. So we can do the same thing, and we have to do the same thing in some occasions in MIPS, right? So when you are running through these MIPS instructions, you are using part of your memory to have certain programs, right? So you have, let me draw this over here. You have register file, right? Here is your register file, 32-bit registers, and then you have memory, right? And in your memory, what do you have? Well, you have a lot of data in there, and you have all your programs in there as well, right? All your instructions are part of the memory. So when you are running these instructions, what could happen? Well, you could have maybe program 1 in some part of the memory. Let me move this down over here so that you can think of it as a big part. And you may have another P2, second program, and then maybe P3, a small program. So your memory can be a bunch of programs. Okay, now these programs or these instructions, set of operations, could have procedure calls, meaning main function could call function 1. Function 1 could call function 2. Function 2 could call function 3, and so on, right? Those are called what? Nested functions. You could have nested functions, or you could just have simple programs. Now, if you want to look at some simple task, okay, everything could be in one program, then it's fine. No need to call other procedures. But if you're looking at something realistic, something that is used for complex instructions, then what will you have? Maybe P1 calls P2, then P2 calls P3, then maybe we come back, right? So P1, when it calls P2, P2 gets control, then P2 when it calls P3, P3 gets control, and after P3 gets done, the control goes back to P2, then the control goes back to P1, right? So that is a scenario, is a realistic scenario where you could have nested functions. Now we need to look at how does MIPS ISA handle all those nested functions. Now, one of the problems that you will get into because of so many programs is what? What are you doing? What are you using to execute these instructions? Sure, you are using ALU to execute these instructions, but you're also using the register file to kind of kick things off, right? So you're also using the register file. Use register file, right? Bandwidth problems. Okay, it could be, but if I say, all right, I don't care about the speed. Can I do it if I just care about getting the instructions done correctly as opposed to quickly, right? I just want them to be done correctly. So if I wanted to do things correctly, bunch of instructions here, bunch of instructions here, bunch of instructions here, all right? For all those instructions, that is a lot of instructions. And I only have what? I only have 32 registers here. Are 32 registers going to be enough to do all the R, I, J type instructions for so many P1, P2, P3, so many programs? Maybe not. You see that? So the limitation is the number of registers. You only have 32. In fact, many of the 32 registers are for specific purposes. For example, we have 4 of them for arguments. We have 2 of them for putting the return values from a procedure. We have 1 of them for used by the assembler. You have 1 of them constant, 0, cannot be changed. We have 1 for the stack pointer. You shouldn't use that as part of the typical instruction. So a lot of these are for specialized reason. The registers that are really kind of helpful, for example, if you're doing add $S0, $S1, $S2, what are you doing? You're adding S1 and S2 and putting the result back in S0, right? So here I'm using register S1, S2, S0. 3 registers right now. You see that? 1 instruction. I have bunch of programs here. So I hope you see that you are going to face a problem with this sort of limitation on the number of registers you have accessible with this MIPS ISA. There is a solution though. The solution is, whenever you need more, store and restore a particular register, right? So if you go from P1 to P2, if you want to use some registers in P2 that were being used by P1, you store them into a different part of the memory, use them, restore it, use the register temporarily. Then before you come out of P2, you restore the contents of that original register. Then you can go back. You see that? So save and restore allows you to reuse the registers. Let me just put down the registers that are going to be of for this use. You have $S0 to $S7, so those are 8. And then you have $T0 to $T9, right? 10 of those. So you have 18 of these registers that are for that are meant for purposes or assistance in executing these instructions. 10 of them are for temporary use, and 8 of them are for the saved use. It has context. It means that your main procedure, your main program will use S0 through S7. Your procedures are going to more likely use T0 to T9. What if procedure needs to use S0? Well, you need to store S0 in the memory first, use S0 for whatever purpose you want, restore it before you exit out. So that's why we need a stack, part of the memory which is used to spill over the register file. So I hope that gives you some background in why we need to talk about a stack. The example of a procedure call is z equals f of x comma y. What are x comma y? X comma y are the arguments that I'm passing to the procedure f, right? So these are the parameters or the arguments. Next, f is what? It's the procedure call itself. Z, what is z? Z is the return value. What registers am I going to pass x and y? One of the 4 argument registers, right? $A0 to $A3. If you go back to your MIPS reference sheet, you can see right here, A0 to A3, these are used to pass arguments. And $V0 and V1, those are for values for function results and expression evaluation. So 2 of them for return values, 4 of them to pass arguments. Next. So when you call a particular function or when you initiate a procedure call, what steps are taken? First, we are going to place the parameters x and y, those are your arguments, in a known place. Known place where? In the memory, right? What else is there in the memory? There is data, there is programs. Now there is a stack, right? Data is used to store maybe operands, maybe some like arbitrary data. Programs, that is instructions meant for a particular purpose. Stack, it is also meant for a particular purpose, and the purpose is well defined. The purpose is to be used as a spillover space for the registers. So the first thing we do, we place the parameters in a known place. Next, we transfer control to the procedure f. Next, we acquire the storage resources needed by f. We perform the task, which means we execute the procedure f, evaluate the result z, and maybe side effects, which means that to go through f, we may have needed to find certain temporary results. Those are essentially your side effects. And then place the result in a known place. What is that? Part of the stack, but these are going to be in the register file, a register V0 and V1, right? So in terms of a register file, they are meant to go in those specific registers. And then once we are through with this procedure call, we transfer control back to our Z procedure, the calling program. So here you have two kind of programs, right? There's a caller and there's a callee. So which one is which? F is the callee or the caller? The caller function is the function in which this is written, right? The callee, yes. So you're calling F. So F is the callee. And the function in which this particular statement is written is the caller, right? So you have main. If main is your caller, if you have a subroutine for something else, then that subroutine is the callee. All right, talked about this. Now let's go ahead with this procedure calls. So what do we have here? The vast majority of procedure calls involve a small number of parameters and results. We are going to try to use registers instead of the stack whenever possible. So if we are able to get away without using the stack, that's good. We can just use the registers. So the number of registers we have, 18 of them, if they are enough, that's good. We don't need to use the stack. Why? Why is this idea a good idea? When you're trying to access the register file, it's going to be much faster than accessing the memory, right? The stack is a space in the memory that is meant to be used as the spillover space. So accessing the memory much slower than accessing the register file. So we are going to try to use register file as much as possible. But in some cases, you don't have an option. You run out of space, you have to use it. So the MIPS convention is this. For use registers for small procedure calls, right? But allow excess parameters and results to spill over to the stack. So if you do not have enough registers, you've already used a bunch of them. Now you need more. So what can you do? You need to first save a register content into memory, use it, then before you exit out of that procedure, you restore the value, meaning pull that information back from memory to the register. The register allocation scheme is this. A0 through A4 used to pass parameters or argument. These are called argument registers. V0 and V1 for return variables, return values. So for example, in our previous one, X and Y were arguments, Z was the return value. RA, return address. It's another address, part of the 32-bit, 32 registers in the register file, but that has a specific purpose again. $RA, which is the return address, it is supposed to hold the address that points to the instruction you need to come back to, right? So when you go from a procedure to something, right? So suppose you are here, right? Suppose you are in P1, and at P1 in the middle somewhere, there is a call to P2, right? So when you call P2, what you do before you go is the next instruction, which is highlighted in blue, that is dumped onto the RA register, the return address register, and then you jump. This is also called the jump and link instruction. That's what that means. So if you see a jump over here, if you see an instruction over here that is calling P2, what you do is you take the address of the next instruction, put it on the return address register, and then jump to P2. Go through P2, and then you can use the contents of RA to come back to the next instruction. Right? So that's the purpose of your RA register. Return address, to return to the point of origin. All right. Jump and link. The thing that I just talked about. It is a special instruction, JAL. There are only two types of jump instructions, jump and link. Jump and link instruction needs a procedure address, which means now I have a 26-bit address that is going to follow the same sort of scheme as the 32-bit address that we talked about earlier. To go from 26-bit to 32 bits, it's the same process. Add 2 zeros to the right, add 4 most significant bits from the program counter, and that would be your total address that you can jump to, right? JAL, that stands for jump and link. It's a type of a J-type instruction. It jumps to the procedure address, but before it jumps, it will link. How does it link? It puts the address of current program counter plus 4 into the return address register. So that is called the linking process, so that once you are done with the procedure call, you can come back to the main program. You know where to come back, right? So as it jumps, it simultaneously saves or links to the address of the following instruction in the register, so which is $RA. RA stands for return register. Now, this also means that I need the last instruction I need in P2 should be a jump register instruction, right? Because I need to jump to this blue line, the address to which is in the return address register. So the last line in P2 would be jump register $RA. That is used to at the end of the return to point to the origin. Let's take a look at this process with a simple diagram. What do you have here? You have a procedure call and return. So this is your sort of the main program, right? This is kind of your main program. Let me call that the caller, right? So this is my caller function, and the yellow one is my callee function, or called function, whatever that is. So I'm going through the instructions in the caller. I get to an instruction where it says, all right, I'm going to have a procedure call, and that is jump ALX. So jump and link X. Okay, so how does that work? The first thing that needs to happen is I need to first preserve the return address. If this is the current program counter, the next instruction is going to be at PC plus 4. We know that, right? It's word aligned. So the next word is going to be PC plus 4. So I need to push PC plus 4 into RA first. That happens first. So now I know where to come back whenever I'm done. I'm going to jump and link. I've linked it first, and then I'm going to jump, which means that I'm going to transfer the control to this particular procedure, the first line of that procedure. X, that's an address. It's a 32-bit address. I've given it a 26-bit address. The 26-bit address gets converted into a 32-bit address, and then the jump is performed. PC equals jump address, right? That's what is done. You go through the procedure. The last line is jump register RA, right? Because you have saved RA with PC plus 4, you know where to come back. You guys see that? So that's your typical sort of call and return. Now you can also see what is going to happen. Instead of 2, you can have 3 and 4 and 5 nested functions. And every time you need to do this, what are you going to do? Do I need RA every time? Here, that's an interesting question. I have only one register. Return address register, I only have one. So if I want to jump and link multiple times, how do I do it? Any ideas? Come on, we know what to do when we need more registers but have only one. Can you use a temp register? No, you guys, right. You need to use stack, right? So what are you going to do? If you jump into procedure and the procedure says, all right, I need to jump one more time, what is it going to do? I'm going to need to put the return address into stack, use it for jumping, and then once I come back to this procedure, I'm going to restore the contents of return address so that I can jump back to 1, right? So this kind of reminds me of that movie. What was that movie? inception, right? So you go from here to here. Now, when you are in the procedure, if you need to use the return address register to jump one more time to another procedure, maybe a subroutine, then you need to put this particular content in stack, use it for the jump between second one and the third one, and then when you come back, you restore the contents of array so that you can make the last jump. You guys see that? So whenever you run into this issue of I need more registers, I don't have them, you are going to have to use the stack to fill up that to work as your spillover space. Now, typically, this is what happens. The caller function tries to use the saved registers. Saved registers. So if I'm using saved registers in my caller, I don't have to push them onto the stack. I can just use the saved registers, S0 to S8. But if my procedure tries to use the saved registers, I need to use them, I need to save them on a stack, use them, then restore the contents before I jump back. But if I want to use certain other registers in the procedure, you use temp registers. So the main function uses saved registers, the procedure uses the temp registers, but here is the deal. The procedure also can use the saved registers, but for that to work, you need to preserve them. So you need to save the saved register, right? $S0. If a procedure wants to use that, needs to save it on top of the stack first, use it during the procedure, then restore the contents, then you can then you are good. You can go back to your main program. All right. Let's see. Talked about this. We talked about that. Now let's go here. Now, there are some other issues here. Suppose you need more registers than the arguments. What are you going to do? Suppose you need more return values than arguments. What are you going to do? Again, the solution is save the registers to be preserved on to a stack. The same discussion that we had for return address register, same applies for arguments. Same applies for V0, V1. You need more, then you need to save the registers, then use them, then preserve them, right? Like restore them. Any additional registers needed by the callee, the function f, must be restored to their original values they had before the function was called. You're essentially going through these steps in order to make sure that the caller doesn't do something that the callee, so the caller and callee, these functions are independently written, right? So the caller doesn't know what registers the callee is going to use. The callee doesn't know what registers the caller is going to use. There is a convention, but they don't know. So if you don't know, the best thing to do is save them, use the register for a particular instruction or bunch of instructions, and restore it. Now let's talk a little bit more about stack. Part of the memory, right? And the idea is it's a data structure for spilling registers. It's a last in first out queue. LIFO, last in first out. What does that mean? That means if you had, say, 3 programs, right? You had P1, come on. Suppose you had P1, and then you had P2, and then you had P3. Three procedures, one inside the other, right? Nested functions. So I'm going to go into P1. I'm executing P1, and as soon as I go into P2, I'm going to do the jump and link, and I'm in P2. When I'm in P2, whatever registers I use in P2, if they are not temp registers, if they are saved registers, I'm going to use the stack. I'm going to put things onto the stack, and now I have P3, right? So if this is my stack, Whatever I need for P1, if I need to push something on the stack, I'm going to push it like this. Then I'm going to into P2, right? And then P2 says, all right, I need to use some more things, and I need to put a few more things over here. So P2 puts it over here. Then P3 says, yeah, I also need some things to be put on stack. So this is how the stack is being filled up by those callees, callee within a callee. But so far we are down to P3, right? What happens after P3 gets done? Well, P3 gets done, it transfers control to P2. What happens then? Well, the stack is last in, first out. So the things that went into the stack last, which is P3, will get removed from stack. So as P3 is finishing up, it also needs to restore the contents from the stack, doing the last in, first out, so that now when P2 gets control back, the stack is the same when it left P2, right? So when it left P2, it was P1 and P2. So when it comes back to it, it should be the same. Now P2 has control. What is it going to do? Before finishing up, it has to move all those values, meaning restore all those values, adjust the stack, remove things from the stack. And then when P1 gets control back at the end, it is the same stack structure when it left P1. Where does it go? What do you mean, where does it go? It just goes back. So suppose I want to store S0 into the stack. I'm going to transfer the contents of S0 into the stack, into the memory, right? Point, and the location in the memory is referred to using the stack pointer. So I'm going to put that on the stack. I'm going to use that S0 register for another purpose. But before I jump out of that procedure, I'm going to restore the contents, meaning from the memory, I'm going to move things back to S0. So restoring the register contents, because I'm done using it. All right, let's move on. MIPS reserves the register 29. The number is 29, which is the $SP, which always points to top of the stack. Stack always grows from higher to lower addresses. Now this particular point can raise a lot of confusion. Let me talk about that over here. So sometimes what happens is, in some literature you will see a high address over here and a low address over here. And in some situations it will be the exact opposite. Low address over here and a high address over here from memory. For a stack, the stack goes from higher to lower. So as it is going, the way I showed it over here horizontally, right? I said stack is growing from left to right. But as far as memory that is laid vertically, it goes from higher to lower, which means first one goes here, next program, next program. So it moves from high to low. However, if you have a memory that is using this particular notation, then it's the other way, right? So it's like, first I'm here, then I'm here, then I'm here. So as I'm putting things onto the top of the stack, I'm putting things more and more on top of the stack. And when I'm going to remove things from the stack, right? Once I restore things to their appropriate registers, I can remove it, right? I need to also remove it. So that would be going down, right? Cutting this out, and so on. So just be careful of that notation. Sometimes it can be this way or this way. Right now we are kind of using this particular format, which is what you are going to see in this diagram here. The high address is pointing at the bottom here, to the space in memory used for the stack, and the stack is essentially going up from higher to lower addresses. So it's going to always point to the top of the stack. In other words, to the lowest register, lowest address in that stack. Now, what happens when you place data into the stack? Well, if you want to place data into the stack, suppose your stack pointer is right here. It's pointing to this location right here. How would I place data on top of the stack? The first thing that I would do is I would subtract 4 from the stack pointer so that it now points to this location, right? So I would do SP equals SP minus 4. When I do that, the stack pointer will be pointing to a lower address. Once I do that, I can place the contents of the register that I wanted to store over here. And as I keep going up and up, I'm moving in the vertical direction. However, more importantly, I'm moving to a lower address every time. Right? Lower address, -4, -4, -4, and so on. Now, that is called placing data into the stack, which is a push operation. And in this case, we subtract from the stack pointer. And we talked about that example. Now, when you want to pull data from the stack, which is called a pop operation, you are doing the other way, right? So suppose you are here. The stack pointer at the end points to the top of the stack. You want to delete this. You want to get rid of this. What do? You move this to the register first, you restore it, then you add 4 to come back, right? So restore means you're right here, you restore, then you add 4 to go to a higher address. So the contents that were saved so that the register could be reused, now they are removed from the top of the stack, and now it is now pointing to the new top of the stack. But that required an addition operation. All right, let's go to the next one here. We talked about this. All right. So what is preserved across a procedure call? And I touched upon this a little bit. So what is preserved and what is not preserved when you make a procedure call? So when you make a procedure call, the saved registers need to be preserved. The stack pointer needs to be preserved. The return address needs to be preserved. The stack above needs to be preserved. All of this needs to be preserved when you make a procedure call, across a procedure call. What is not? When you are in a procedure call, you can use the temporary registers. You can use the argument registers. You can use your return address registers. You don't need to preserve them across a procedure call. Now, if a procedure call has another procedure call in it, then this needs to be preserved as well. Right? So I hope you guys see how this is going to work. The goal should be not to contaminate the contents of any registers because of procedure calls. All right. Here we have an example. Here we have a example is the name of the procedure, and the arguments are GHIJ. The return is F, which is your return value. What you are doing is you are initializing F as an integer. You are doing a simple arithmetic operation, G plus H minus I plus J. So you are going to need a bunch of registers to denote the variables G, H, I, J. Then you do that particular arithmetic operation, compute F, return the value of F to the caller program. That's your subroutine example. Now what we are going to do is, here we have a C code. Our goal is to write the MIPS code for this. And in order to do that, we are going to do this. GHIJ, we are going to use, right? These are all arguments that are being passed or parameters that are being passed. to that particular procedure called example. So we are going to use A0, A1, A2, A3 as our 4 argument registers. The local variable that we are going to use inside the function itself is S0. Is this a good choice or a bad choice? What would you, if I did not use S0 and I left you the choice to use a variable locally inside the example procedure, what would you have used? Come on. S0 is T0, right? Absolutely. So I would have used T0 because it's a temporary register and the caller doesn't need to save, the callee doesn't need to save that. I can use that temporary register inside my procedure call. But so S0 is a bad choice, right? In that regard, because I know the caller function is going to be using that saved variable, which means before I use S0, I need to save it on top of the stack. So here the choice is bad only because I want to demonstrate that there is a need to push it on top of the stack and pop it from top of the stack at the end. And then the return value for F is in V0. Let's go through this. So here is our example routine in C, and we have a MIPS code at the bottom here. So what are we going to do? Our stack pointer currently points to the top of the stack, which is maybe right here. Now, the first thing that we do is when you go into this procedure, because of some jump and link instruction being executed, the first thing that you need to do is, because you have plans of using S0 as a local variable, you need to put S0 on top of the stack, right? That's the first thing that you need to do. So before, where are you going to put it? Right now it is pointing to the top of the stack. So that address is already taken. So the first thing that you do is actually subtract 4 from the stack pointer, moving it up by 1. When you move this up by 1, you have a space in the stack that is meant now to store whatever variable you want to store, whatever register you want to store. Right? So move first. How are you moving? You are subtracting immediate 4 from stack pointer, and you're putting the result back in the stack pointer. Stack pointer is a 32-bit register in the register file that contains an address. What is that address? It is address pointing to the top of the stack. The stack goes from higher address to the lower address, right? It's right now here. It'll go here now. The first question is, how many things do I need to store? Well, I only need to store S0 because I'm only going to be using S0. If I was using S0, S1, S2, like say, for example, 3 registers, then I would have had to move by 4, store S0, move up by 4, save S1, move up by 4 again, save S2, right? I don't have to do all that right now. I just have to do it one time. Subtract immediate 4 from SP, put the result back in SP. That essentially moves the stack pointer up by 4, which is the next word. I'm going to store the word now. What is that? Offset is 0, address is in the stack pointer, S0 is your register that you're trying to store. So what does that do? That essentially puts S0 over here, right? 32-bit contents of register S0 are now placed on top of the stack. Saved saved register S0. Store word. Next, we are going to do this add, subtract, add. What are all those meant for? Those are meant to carry out that, right? Now, I'm not going to go into the details of this because it's very easy here. Add, subtract, add. That's simply add, subtract, right? And then at the end, you are adding because you want to put the result into that return variable, the return register V0, right? Like that's the last step there. So what actually yeah, those three are mapping that. The thing that I want to point out is this: I used T0, didn't have to store it on top of the stack. I used A0, A1, A2, A3, didn't need to store that on top of the stack. I used S0. I did need to store it on top of the stack, right? That kind of relates to this. What needs to be preserved and what doesn't need to be preserved across a procedure call. Now, this is in the context of one guy calling the other. Now, if one guy calls the second guy, calls the third guy, calls the fourth guy, then this will apply to the previous guys as well, right? Next, we did this, and then after we are done, what do we need to do? We need to get rid of this S0. We saved the S0 from, we saved it because the caller function would have probably been using S0. We didn't want to change the contents, so we saved it first. Then we used S0 for our example procedure. Then now what do we need to do? We need to load word, meaning whatever you have in this address, which is the current stack pointer, load it back into S0. So this is restoring the contents of S0, which means this gets moved to S0, but I also need to get it out, right? Meaning get it out, meaning I just need to adjust the stack pointer so that it moves down. I do that by adding 4 to the stack pointer. So now it's going back to this. You see that? So hopefully that gives you an idea about how to work with a stack and how it grows and all that. We have addressing modes that are next, but I'm gonna talk about addressing mode in the next lecture. We have a couple of slides, so I'll finish up this lecture when we meet again on Thursday. But you guys should be okay to do the activity. Hopefully it's not too bad this time. Two simple problems.